time for us to spend some quality time getting to know the Std Set Type. So unlike vectors and lists, which implement the abstraction of a sequence, where we can add a bunch of elements and the order of those elements is preserved, a set is a collection. So it's one of our standard collections, but it's not a sequence. We can add all sorts of elements, but we're no longer in charge of their ordering. As we've seen before, the ordering is ascending order of the element type. But, of course, that's because sets have been optimized to make other operations more convenient. For example, searching for elements. We need to see how to use all of these operations. One key outcome of this, though, is to understand that just because I said sets are fast for searching doesn't mean that every possible way that we could search them is going to be fast. We have to use special techniques to search the set using the optimized searching. So the way we've been searching collections so far has been for things like vectors and lists, iterating over the collection with a loop and then asking if each element is equal to what we're looking for. You can do that with a set, but it's not fast. That's just as slow as it would be on a vector or a list. We have to call special functions to do the search operation over a set. So what I have here is a set of strings. It's called fruit. And then I've got 8 insert statements, and each one is adding a distinct element. So there are 8 separate things being added to this set. Notice that I'm using dot insert and not dot push back or push front because it wouldn't make any sense because obviously I'm not in charge of the ordering. I just say add this element to the set. Also notice that dot insert exists for vectors and lists as well, but on a vector or a list, you have to provide an iterator to dot insert to tell it where you want the insertion to happen. Although you actually are allowed to do that on a set, it doesn't really do anything useful from our point of view. It makes sense because you don't get to be in charge of the ordering that you shouldn't have to provide an iterator because why would you need to? So instead you just give it the element and it throws it into the set. And one other thing to observe is, as we go forward with more and more of these standard collections, you will notice that, of course, a consistent interface exists to the extent possible. And so I actually think if you pause the video right now, you probably could write tasks 1, 2, and 3 without seeing the code I'm about to write. You could probably deduce from the context, from the other collections you've seen, how to do tasks 1, 2, and 3. Okay, so I assume if you were going to try that, you already did it and came back, so let's go through this ourselves. So I want to print out the size of the set. So the size, actually we'll print this as task 1. Task 1, the size is, and then I print out fruit.size. There it is, and we'll just start with that. All right, the size is 8, and sure enough, there were 8 insert statements for 8 distinct elements. Task 2, add the same element over and over again and then print the size. Okay, well, if I'm going to have duplicates of anything in life, it's going to be raspberries, so we'll just add 4 more of these. We'll try inserting the key raspberry over and over again, and then we'll print out the size again. And the point I'm trying to drive home here is that on the data structure we are using, the original Std Set object, it turns out duplicate elements are not allowed. And so if I try running this, I will observe that when I print out the size after doing the duplicate insertion, the size is still 8. I can add as many elements as I want, but if I add an element that's already there, basically nothing happens. The set just stays the same. I cannot add more than 1 copy of a given element. We'll see in a minute that there are actually other variants of the set that do allow this. There is something called a multiset, which you might notice queued up at the top of my screen. But the regular Std Set Type doesn't. Okay, task number 3. I want to iterate over my set using a for each loop. Okay, this is something we should be familiar with. So we know already from the beginning of the semester that for each loops can be used to iterate over our collections. We also should recall that strange legalese that I used when I introduced them, which is when I use a for each loop over a collection, the order that I get each element is the natural ordering of its contents. And I'm sure when you watched the video or saw the lecture or whatever about vectors and for each loops, you thought, that's a bit suspicious. Why don't we just say that we iterate over the vector from left to right? What's all this business of the natural ordering? Well, it was sort of setting us up for this moment, which is that for vectors and lists, where we define our own ordering, of course the for each loop goes in that order. But what about cases where we don't get to define the ordering of the elements? In that case, the collection decides which order to give you back the elements. And it will always be the same, deterministically defined order. But of course, the collection might change the order between insertions or something, but you do actually know what order it's going to use. There is a natural ordering that each collection uses. And for the set type, the ordering will be the ascending order of the underlying element type. And so we'll try printing that out. The loop we end up using, though, is exactly the same as the one we would use to iterate over a vector or a list. That's one of the great conveniences of for each loops. And here we are. So if you take a look at the insert statements, you can see that I insert raspberry first and orange last, and yet when we're done, raspberry's near the end and orange is stuck in the middle. But of course, the elements are now in ascending order of the underlying type. And of course, for strings, if I compare two strings together, if I ask the question, is this cranberry less than orange? The answer is yes, because the natural comparison for strings is alphabetical order, or dictionary order, or formally lexicographical order. So that is, cranberry is considered less than lemon because cranberry would appear first in a dictionary. Okay, so I've printed out the contents of the set, and now it's time for us to learn about that fast searching logic. So I've mentioned that one of the benefits of using a set is you can search for an element really fast compared to what you would do over a vector or list. To take advantage of the fast search, though, you actually have to use special functionality. So I'm going to begin by writing what I think is the obvious way to search for an element. So a set can only contain one copy of each element. And so for our purposes, that means that to search for something with a set of strings, all I'm really doing is asking yes or no, is the element there or not? Any other information I might want to know if I were searching a vector or a list wouldn't really apply here. Information like, what index does the element appear? Well, there aren't any indices on a set, so why would I care about that? So just to ask the yes or no question, is the element there? I can use this function .contains. .contains returns a bool, so a true or false value. And if the element is contained in the set, then it returns true. Oh, whoops, I hit page up there. Okay, so I'm just going to write a quick if statement here just to print out the two cases. So the set contains the element lemon. And then we'll add something to the else case. So as we can see from the output and from our insert statements above, the set does contain the element lemon. But I want to create sort of a common test here that I can use for other things. So to verify that we know how to use .contains, we should try searching for something that is there and try searching for something that isn't there. So the word lime. And if all goes well, we should see in our output that the set does contain the element lemon and the set does not contain the element lime. And there it is. It contains lemon, does not contain lime. So that is the, I think, orthodox way in C++20 for like this video of searching a set. What's really bizarre about this is such a simple function, just yes or no is the element there. This function wasn't actually added to the language until C++20. So if I were using C++17, I wouldn't have .contains at my disposal. And because it takes a couple years after a new standard is published for compilers to get up to speed and for operating systems to include those compilers, when I taught this course in 2021, so that's after 2020 in case you were wondering, when I taught this course in 2021, we were still using C++17, and that meant we couldn't use this sort of obvious, natural, convenient way of searching. We were stuck with using one of these two methods. And actually, although this looks pretty convenient, we'll see in a minute, it turns out the sort of orthodox way of searching sets was this version down here, which I will go over because you're going to see it out there on the internet or something. But it's pretty ugly looking, and it involves iterators. And we know by now that we'd like to avoid using iterators unless we absolutely have to. So I'm going to do the same search in two other ways. Task 4b is going to use a function called .count. So the .count function, which has existed since before C++20, the .count function tells you how many copies of that element were found in the set. And obviously you can stare at that and say, what the hell is that for? I mean, the set can only have one copy of each element. Why would we have a function to count how many copies there are if we don't have a function just to answer the question whether there is an element or not? The reason is because this is for symmetry with a different data structure, the multi-set, which could contain duplicate copies of an element. So .count is another somewhat convenient way of searching for an element. If the count is greater than 0, then the element is in the set. If the count is equal to 0, then the element is not in the set. So we'll try that out. We can see we've printed the same thing twice here, but the set contains lemon, doesn't contain lime, does contain lemon, doesn't contain lime. Okay, task 4c, and this one's really sort of unnecessary these days, but we'll see that there are applications of this .find function, just not really for the basic search application. So the .find function takes an element and it returns an iterator. The iterator, if the element is found, the iterator that it returns will be positioned at the element that it found. If the element is not found, it returns the invalid .end iterator. And that means we could use the return value, because we're allowed to compare iterators, we can use the return value as a way of gauging whether the element was found or not, of doing that search. And so a typical way of using .find to search a set would be to ask the question, is the return value of .find equal to the .end iterator? And if it isn't, that means that the element was found. So if it is equal to .end, the element wasn't found. So I'll try this. I'm going to hope my copying and pasting doesn't come back to bite me. There we go. And now we have 3 copies of the same output. So I have now searched for the element in 3 different ways. For asking the question, though, of just yes or no, is the element there, I think we can all agree, frankly, that .contains is the easiest way of doing that, the most convenient. Okay, 2 other things. I want to delete some elements. And I think at this point what I'm going to do is I'm going to print out the entire set at the very end, just so that we can see the effect of these deletions and insertions I'm about to do. So I'll do that, and we'll just test out that that loop works before we go any further. Okay, so then I've just done my searching. Here's the set when I'm done. Task number 5 says delete some elements. We saw earlier that with a set, .insert doesn't require an iterator because obviously you don't care about the position of an element in a set. You can also erase with .erase without using an iterator. So fruit.erase, I'll erase the value lemon, and I will erase the value grapefruit. And we'll just see what happens. So you'll notice task 5 says attempt to delete. And what I want to observe is the element grapefruit isn't actually in the set. So I'm trying to erase something that isn't there at all. And there's a few ways you could interpret that. Notice that when I do this, the operation apparently succeeds. So I did delete the element lemon, it's gone, but the element grapefruit is still not there. I mean, it wasn't there to begin with, but the erase operation didn't give me any kind of an error. It didn't throw an exception or anything. And so I'm saying attempt to delete. So .erase, if you give it a key that isn't in the set, it just does nothing. And if that bothers you, it turns out that there is actually a return value from .erase. And if you wanted to, if you cared whether the delete operation did anything, you could take a look at the return value. So I could say deleting lemon. And the return value is just an int. It's just a numerical value saying how many copies of the element it deleted. So we'll say the number and then elements removed. And I will do the same thing. I will sort of cherry pick and copy and paste here a bit. And I can do the same thing for grapefruit, and we can observe that we can use the feedback that .erase gives us to know, if we care, whether or not it actually deleted something. Now, that said, in practice, like on an exam or something especially, if you want to know whether the deletion is going to succeed, you could always just search for the element before you delete it to decide whether it's there or not. Keeping in mind, if the element's there, .erase will delete it. So there's no other reason that the deletion would fail besides that the element isn't there. So in general, even for task 6, if you want to know whether or not an element is already in the set, you could just search it. There's no requirement that you learn to use these return values. So you don't have to, I don't know, uphold the same standard that I do. For completeness, I have to talk about these methods. Although I would encourage you on an exam or something, if you want to know whether something's in the set, learn how to search the set and do that, because you're going to need to know how to search the set anyway. So I'll try this and see what happens. Okay, so we can see deleting lemon, it removed 1 elements. I don't like that plural. And then deleting grapefruit, it removed 0. Okay, so the .erase function did give us some useful feedback there. And then finally, let's talk a bit more about .insert. So if I run something like this, we already saw that obviously I can call .insert on elements that are already present. So we know that raspberry is already in the set, and it shouldn't surprise us to learn that, like we saw above, if I do a second .insert, raspberry does not get added again. We just keep the existing version and nothing else happens. And so if you care, so if you want to know whether the insertion succeeds or fails, that is, if it actually adds a new element to the set or not, you have a few options. One of them, again, is just look for the element before you insert it. If it's already there, then the insertion won't do anything. You could also check that the size of the set increased after the insertion. That's a sign that the insertion did something. But finally, there is one other way of doing it, and it's, frankly, you might use this on an assignment, but I don't know whether I'd encourage you to memorize this for an exam, because it's a bit, I don't know, it's not very much fun to write, and it's error prone to try and remember it. The .insert function does return something. It returns a pair. To be clear, what it actually returns is this object of type std pair. The elements of the pair are complicated. So the first thing is an iterator. And the second thing is a bool. So dot insert returns a pair where the first element of the pair is an iterator, and the type of iterator, as we've seen before, is complicated. And the second thing in the pair is a bool. So what I'm going to do is, instead of writing this out, I'm of course going to take advantage of the fact that I'm allowed to unpack pairs using the auto keyword. So I'm going to call this iter1 and insertion succeeded 1. So the second element of a pair is a bool, it is true if the insertion did something, so if a new element actually got added. And of course, if a new element got added, that means that the element you were trying to add wasn't already in the set. The bool is false if the element was already there, and therefore that the insertion did nothing. And so I'm going to do the same thing down here with this. I'll call this iter2 and insertion succeeded 2. And so dot insert does give us some feedback to that extent. Although, as I said, if you really cared that much, searching the set before you insert might be an easier way, a cleaner way of doing that too. But this is a way of, I guess, not duplicating work as much, which is a concern in some contexts, not so much in this course. Okay, so I was inserting the value lime, and if the insertion succeeded, if something actually happened, that means that lime wasn't already there. So the value was not already present. And then the alternative was if I tried to insert the value lime and the insertion and this came back as false, that means the insertion did nothing because the value was already present. So we do value was already present. And then I will just steal this and use this for the second case as well. So that would be insertion succeeded 2. And the key I was trying to insert there was raspberry. All right, and we'll give that a try and see what we think. And observe that when we're done, lime is in our set. When I tried to delete lemon, it did delete something. When I tried to delete grapefruit, because grapefruit wasn't there to begin with, it didn't delete anything. When I inserted lime, the value was not already present. The insertion succeeded. Something actually happened. When I tried to reinsert raspberry, nothing happened. The insertion, I guess you could say it failed. The insertion was unnecessary because the value was already there and you're not allowed to have duplicates. So a defining feature of sets is that duplicates aren't allowed. That means that even if you don't care so much about the fast searching, you can often use a set as a clever way of boiling down some collection to remove all of the duplicates because the set doesn't allow them. And also because it silently allows you to run dot insert over and over again, you don't have to worry about complicated error handling or anything if you want to add a bunch of elements where some might be duplicates. Okay, so what are some other options here? I mean, I guess one of them is, how do we get around that no duplicates requirement? There are reasons why maybe we do want to have duplicates. Another one is, what is an unordered set? So in a future video, I'm going to show off why an unordered set can be a little bit faster than a regular set. The reason it's faster is that we are trading off search time, so we get better search time, in exchange for not getting any particular ordering of elements. I mentioned earlier this idea of the natural ordering of the collection. For a set, a regular STD set, the natural ordering is the ascending order of the element type. And the natural ordering of a collection, so if I ask the collection to give me its elements in their natural ordering, it is in control. The collection does get to decide what its ordering is, and it does this deterministically. The ordering might change, though, between insertions or between modifications of the collection, but the collection gets to decide when that happens. An unordered set, true to the name, has a natural ordering that makes very little sense to an outside observer, and I'll try and show that off. It's important to understand, though, that the ordering isn't truly random per se. Internally, the elements are being kept in an organized way, just not in a way where the ordering is very useful outside of the set, or maybe even like very easy to parse. Like it's not obvious why they're ordered in a particular way. Actually, I'm using sort of a longer form loop here. I'm going to change this to be more congruent with what we already had. So I'm going to print everything out in one line. There's a certain hazard you run trying to modify your materials in the middle of recording a video. Okay, so there we go. We print out all the elements of the set. So I add the elements. They are not added in alphabetical order. And when I print them out, they are not printed in alphabetical order or in an order that really reflects the order that I added them. Maybe by coincidence, there are some elements like raspberry and pear that are still next to each other. But otherwise, it's sort of an arbitrary ordering. But let's try something else. Let's try adding some more stuff and then printing the set out again. So I have to be careful to add fruit that isn't already there. We'll add lime, and then we'll add grapefruit. And actually, maybe I want to, just in case, we'll add cantaloupe, and and try printing it out again. So what I want to show off is that the way that these unordered sets maintain their elements isn't just a sort of an odd jumble, but that we can't really count on it at all. Okay, so we can see here, I just added lime, grapefruit, and cantaloupe. So I print the set out once. I get lemon, guava, strawberry, cranberry, orange, pineapple, pear, raspberry. I then add lime, grapefruit, and cantaloupe grapefruit go at the beginning of this resulting sequence, and then lime ends up sort of buried in the middle somewhere. And of course, internally, there is some logic to this. We just don't have any way of knowing what it is. I'm going to try one more example where I remove a bunch of stuff and I build the collection up a bit slower. So here, the collection is going to end up with 7 elements, but I'm going to print it twice, first after 4 and then after the other 3. So here I get lemon, orange, pear, raspberry. When I add those 3 elements, this time they all end up apparently at the beginning of the natural ordering. Notice that this just seems completely arbitrary. Before, lime got folded in somewhere in the middle, and then after lime, all 3 of the new elements ended up at the end. So we shouldn't assume anything about this. We know that it's keeping its own internal ordering, but we shouldn't count on the ordering having any particular logic at all. And so because the set is maintaining some internal organization that is optimized basically entirely for inserting, searching, and removing quickly, and not worrying so much about maintaining some consistent view as time goes by. So we'll see later, I hope to justify later the benefits of an unordered set, like why it actually is faster and therefore why we should use it if searching is our biggest priority. And then finally, what is a multiset? So this is a regular STD multiset. There is also such thing as an unordered multiset. So there is a set, an unordered set, a multiset, and an unordered multiset. So what's the difference between a set and a multiset? Well, the main difference is you are allowed to have duplicates. So here I've got a set. I start off with one element, pineapple. Then I add raspberry 4 times. Then I add apple 4 times. And then I print everything out. And then I show off a couple of the other differences between sets and multisets. The key thing here, the set is called S in this example. The key thing between the set S in this example and the set of fruit in my initial example, although both things support the same operations like .erase and .count, the operations are much more useful in some cases for the multiset because something like .erase actually could, remove more than one copy. We saw earlier it was a bit bizarre that we would, .erase returns either 0 if it didn't remove the element or 1 if it removed it. In a multiset, it could remove 0 copies or 1 copy or 10 million copies. So the return value of .erase now is a little bit more relevant. So we'll try running that. All right, so the initial contents are 4 copies of apple. This is a multiset, not an unordered multiset. So this multiset maintains its elements in alphabetical order. So 4 apples, banana, peach, pear, pineapple, then 4 raspberries, and a strawberry. If I call .erase on the key apple, then it returns 4. It deletes all of them. So if I pass in a particular key to a multiset's .erase function, it goes through and cleans out every occurrence of that element. I guess I should also demonstrate what .count does. So we'll do this down at the bottom. I guess, congruent to how .erase returns the number of elements, I should also try and print out I should show off that .count can also do that. Let's see, occurrences of raspberry. So I'll call .count, and on a multiset, again, .count is a lot more useful, I think. So I'll call s.count and then raspberry. There we are. In the meantime, before I do that, I want to show off one use of .find. So we saw previously that if I use .find to search my set, then I might not know what I'm doing. I mean, why would I bother using .find, which gives me an iterator, when I could just use .count, or I could use .contains to ask the simple question, yes or no, is this element present? Well, in a multiset, I might have multiple occurrences of a particular element. There could be a time that I say, okay, there are 4 raspberries in this multiset. I want to only talk about this one. I want to refer uniquely to this occurrence of the element raspberry. And that's one reason I might use an iterator, because I could position an iterator at any element of the collection. So even the second out of 4 raspberries. One reason I might want to do that is I might want to delete one occurrence of raspberry. Not all of them, just one of them. If I use .erase with a key like apple, I remove all of them. If I just want to remove one of them, I could use .find. .find goes and finds me an iterator to one occurrence of the element I'm looking for. Now, of course, it could also find nothing, and then it returns .end. If it returns a valid iterator, then I can pass that iterator into .erase. Now, the difference here is when I use .erase with a key, like a string, then .erase deletes all of the occurrences of that key. When I use .erase with an iterator, I'm telling it, I want you only to remove this one element, the same way that you'd remove it if I were moving from a vector or a list. If I pass in an iterator, only that one thing gets deleted. And so this is a way of removing only one occurrence of a particular key, using .find to get an iterator referring to that to one occurrence of that thing, and then using .erase to delete the element at that point. The comment here is pointing out that the actual type of the iterator is this. Recall that the types of iterators are pretty cryptic because the type of iterator depends on the type of what you're iterating over and the element type that you're working with. So it's actually filed under multiset of string. And then I print out the number of occurrences of raspberry. So at the beginning there were 4 occurrences of raspberry. I then delete one of them. So when I'm done, there should be 3 of them. And so I'll recompile and run this now that I've added that call to .count. All right, so I delete one occurrence of raspberry, then there are 3 occurrences left. I print out the multiset. There are no apples left. There are now 3 raspberries and everything else is intact. So a multiset gives us all the same operations as a regular set, except duplicates are allowed. And we find that is often useful, but it turns out it's surprisingly useful to have the no duplicates restriction of sets, because there are lots of cases where we want to search for duplicates or where we don't care about how many times an element occurs, and therefore it's sort of better for us to reduce clutter by limiting the number of occurrences to 1.